What powers your favorite gadgets? The electric motor? Nope. The brakes? Nope again. That sleek, glossy body? Not quite. The real heart of your EV, smartphone, or laptop is the battery. The unsung hero delivering the juice to keep everything running. You can think of it as the motor of your Tesla or the soul of your iPhone. Why? Who does not want a smartphone that can keep you connected all day, or an electric car that zips around town without a single drop of gasoline? Imagine if our devices had personalities. Our smartphone would be like that overachiever friend who's OCD about everything: emails, messages, social media. But without its battery, it's like that same friend after an all-nighter, completely useless. Or think of your laptop as a high-performing executive at work. It attends meetings, crunches numbers, hosts conference calls, streams YouTube all at once. But take away the battery, and it's just a fancy junkyard. Lithium-ion batteries make all this possible by offering a compact, lightweight, and highly efficient power source. But have you ever wondered how these batteries are made on a massive scale? What's inside them that charges your EV, mobile, laptop, wearables, and all the gadgets you can't live without? Let's find out. Picture a Willy Wonka factory, but instead of chocolate rivers and Oompa Loompas, we have chemical reactions and automated assembly lines. It's where science meets engineering with a dash of magic, minus the golden tickets. But how does this small thing power electronic products? Well, stick around. We'll need to look at how these batteries are made. Spoiler alert, this involves more chemistry than your high school science class, but without the pop quiz. Ever thought about the journey lithium takes before it ends up in your battery? It starts with raw material extraction. Picture Indiana Jones. But instead of ancient relics, we're hunting for lithium-rich ores. We dig deep, open pit or underground, to unearth this treasure. Once extracted, the ores are processed to get lithium carbonate or hydroxide. Wait, you know who invented lithium batteries? Who was good enough in chemistry to create this groundbreaking feat? The right answer will earn a shout-out from us. And here is the biggest clue. The name of the inventor is hidden in the question. So, who is smart enough to find that clue? Hurry up while we move on to the next stage of the process. Lithium, the rock star of our story, needs a good wash. It goes through dissolving, filtering, and polishing until we get pure lithium carbonate. It's like taking your dirty car through the deluxe wash at the car wash, wax and all. And it's not just lithium we're after. Depending on the type of battery being made, we need a whole grocery list of other materials. Tesla, for instance, besides using lithium iron phosphate, or LFP, it also uses nickel cobalt aluminum, NCA, or nickel cobalt manganese, NCM. On the other hand, the newest blade batteries of BYD use lithium-ion and phosphate composition. For cathode materials, you know it depends on the composition you're after. Lithium cobalt oxide, LiCoO2, lithium manganese oxide, LiMn2O4, or lithium iron phosphate, LiFePO4, are used for cathode materials, whereas graphite mixed with binders and coated onto copper foil are used for anode materials. To boost performance, we add a protective layer and performance enhancers. Separators like polyethylene are used to split them apart. But what happens after we gather all these ingredients? That's where the real magic begins. Slurry preparation, just like you make cake batter, but instead of flour and milk, you add binders and solvents to create a slurry. This secret sauce gets spread on electrodes to make them work. And just like you mix your cake batter to avoid lumps, here mechanical stirring or ball milling is used to blend the slurry nicely. Sometimes for a top-notch mix, ultrasonication is used. Once our slurry is smooth, it's time for coating. We slather it onto current collectors using techniques like Dr. Blade coating. It's a bit like spreading frosting on a cake, but with more precision. But how do we ensure these layers stick together perfectly and function well? Let's move on to the next step. After coating the electrodes with a slurry, we need to dry them out. This means heating them up to make the solvent evaporate. It's like giving the electrodes a hot bath to get rid of all the excess moisture. Once they're dried, we move on to the calendering. This step compresses the electrodes under high pressure, giving them a firm squeeze to make them denser and improve their performance. Calendering also helps get rid of any leftover solvent and ensures everything is tightly packed so the electrodes can do their job efficiently. Think of it as the electrode's finishing touch, making sure they're in top shape for high-quality battery action. How do these finely pressed electrodes become a working battery? Let's stack things up. Time for the battery to take shape. Assembly in formation. First, we stack up the battery's inner parts. Imagine laying out slices of a sandwich, alternating between positive and negative layers with some separator material in between. Separators are like bouncers at a club. They only let the VIP ions through while keeping everything else in check. Finally, we add the electrolytes. But what are they? The secret sauce of our battery sandwich. It's a conductive solution that helps ions move between electrodes. This step needs a careful hand to avoid leaks or air bubbles. What's next once our tech sandwich is assembled? Time to suit up. Once this tech sandwich is prepared, it's wrapped with a well-fitted suit of armor. First, the outer shell is welded shut, then insulation is added around the welds, and a final protective coating is then applied to shield the battery from moisture and corrosion. It's like wrapping your sandwich in foil and then putting it in a Tupperware. We're all about that double protection. Moving on to the formation cycling. This is where the battery gets its pre-season training. Charged and discharged repeatedly, the battery's internal components are activated and any potential weak spots are identified. But how do we ensure this armored battery is ready for the real world? Let's put it to the test. The final stage is the thorough quality check, where each battery undergoes a rigorous test, like a test drive for a car. We check for voltage stability, charge capacity, and cycle life. And just like making sure a car won't break down on a road trip, we test for safety, including extreme temperatures, overcharging, and short circuits to make sure the battery doesn't throw a tantrum. Once the tests are done, it's time for the grand assembly. Cells are meticulously put together into battery packs, with special attention to design and electric connections. So that's how lithium from the deepest ores turns into the tiny powerhouses that keep the biggest EVs zipping down the road. Magic? Maybe. Engineering? Definitely. While most battery makers stick to the classic formula, BYD, a Chinese automaker, has flipped the script with their Blade battery, and it's shaking up the electric vehicle world. Instead of the usual rectangular cells, BYD has gone for this sleek, blade-like design. But this design isn't just for looks, it's all about performance and safety. By increasing the contact area between cells, the Blade battery efficiently transfers heat and reduces the risk of a meltdown and a crash. It's a sleek and tough cookie that can handle a lot of pressure. Did you know BYD even tested these batteries by placing a 46-ton truck on top? Yes, a truck. What happened? Nothing. The battery stayed cool and intact, and in fact it was reused in the vehicle. Unbelievable, isn't it? Did you know the global demand for lithium-ion batteries is skyrocketing? It's like the latest iPhone release. Everyone wants a piece. By 2030, the electric vehicle market alone is expected to account for more than 60% of the demand for lithium-ion batteries. That's a lot of Teslas zipping around. Speaking of Teslas, Did you know Tesla's Gigafactory in Nevada is one of the largest buildings in the world by footprint? It's like having 100 Walmarts stacked together, all dedicated to cranking out batteries. And they're not just making batteries for cars. Tesla also produces power walls, home batteries that can store solar energy. Imagine a world where every home has its own personal energy reserve. Pretty cool, right? The consumer electronics industry is another major player. Think about all the gadgets we use daily: smartphones, laptops, tablets, smartwatches, and even electric toothbrushes. All of these devices rely on lithium-ion batteries. In 2020 alone, over 1.5 billion smartphones were sold worldwide. That's almost one for every 5 people on Earth. What makes lithium-ion batteries so efficient for mass production? It's all about energy density, the amount of energy they can store relative to their size. They pack a punch in a small package, making them perfect for everything from tiny earbuds to massive electric trucks. Plus, they have a long cycle life, meaning they can be charged and discharged many times before losing capacity. It's like having a rechargeable flashlight that lasts for years. But wait, are lithium-ion batteries the green superheroes we hope they are? Sadly, no. They're still working on their eco-friendly cape. Lithium and manganese are plentiful resources, with lithium reserves standing at around 21 million tons. Theoretically, this can support the ambitious transition to electric vehicles, EVs, projected for the 2030s to 2050s. But the real plot twist comes with nickel and cobalt. Did you know that 2/3 of the world's cobalt is sourced from the Democratic Republic of Congo, a region fraught with environmental and ethical concerns? Cobalt itself is a highly toxic heavy metal, raising serious issues as demand skyrockets. Besides, electronic waste is another monster lurking not only behind the walls, but on the roadside, streets, streams, rivers, and anywhere else where it should not be. Today, just 5% of the lithium batteries are recycled. Where did 95% of the used batteries go? What happens if the flammable electrolyte within them gets somehow exposed to the air? So these are the areas that still need attention, innovation, and of course environmental consideration. We need better systems for recycling and reusing these materials to make the whole process more sustainable. But overall, it's exciting to see how far we've come with batteries and anticipate what's next on the horizon. Lithium-sulfur batteries and solid-state batteries are already trying to make a move. But what about an AI lithium hybrid? Maybe a lithium-air combo where lithium reacts with air to generate electricity? There's a vast sea of ideas, but can they ever turn into reality? Share your thoughts in the comments section.